going to go from here. I'm going to quickly elaborate what's happening here. So why I want to get this out of the way. This is just the basic operations like addition, subtraction, all that stuff. Models are just basically, let me show you guys something. So these are the, like, obviously these are the 2D arrays, and then we have the operations and the models, right? So let me show you guys something really interesting. So over here in this code, right? So this is the tensors that we're creating. So pretty much once we have these, like the tensors, what we do is, for the x-axis and the y-axis, we have a sequential model. So this is like inputs, okay? So let me show you guys. Inputs directly flow to the outputs in the sequential model. So that's like the easiest model. So input directly goes to the output, and these are the layers, okay? So the layers, there's two ways of approaching this. So the first way is obviously you have a first layer. So this is in order for like the perceptrons. Perceptrons are like the equation is xn times wn times pn, which is the inputs times the weights times the bias. Okay, so each layer is basically like a perceptron, and the sum of the perceptrons is basically compared against an activation function to either result in true or false. Okay. And this optimizer right here goes and adjusts the weights of the what do you call it, the W, and then pretty much reduces the MSE. So the MSE is basically the result, the calculation of how much of a loss is incurring. Now epochs over here is obviously the number of times it's going to keep doing something over and over again to reduce the loss with higher number of times, like higher number of iterations, right? So this is basically the number of iterations right here. So this function is basically, this is just a callback function, but this, what we're having here is the actual data plot here. So once we have that, we're calling this function. So in here, we're pushing, so what we have here is the max number, right? So that's what we're iterating to from starting from 0. So we're pushing onto this array right here, and then we're also pushing this number right here. So where is it? Where's the number? So this one, right? We're pushing onto the y array, and then we're plotting. So if it's equal, if the iteration is complete, that means equal to 10, then we plot the data on the, so just to see the relationship, I think. So over here, what we're going to do is I'm going to show you guys something interesting. So obviously we know we need to normalize the data first, and before that you need to obviously clean the data. So we get the data to x and y axis, you clean the data, and then you pretty much fetch the data, and then you get this to one value. And once we do that, we have the values over here, and then this is the surface. So this right here is wiser. So TensorFlow wiser. That's what we use to plot, and we're using the actual values to plot the data, right? So what we're going to do here is we're going to have the original and the predicted. So first, before that, so these are just the labels that we highlight over here. So it's nothing confusing. So it's just the horsepower and the mass per element. Okay, so that's what we see here. So so over here we're just doing this to shuffle the data. Otherwise, it's going to spit out like a parrot. And we need to convert them to tensor. So that's like arrays, and so those like matrices, but in code. And apart from that, you need to normalize the data. So normalization needs to be done. So it gets it in like closer range, right? So 0 to 1 is like the using min max out from exactly. So what we're going to do here is we're going to normalize the data. Okay, so this is the important part. So let me show you guys something. Okay, so right here we have the sequential model, right? So this is what we have over here that we're calling. So once we do that, we add two layers. So the first layer is obviously this is the x, and then this is the w, and then this is the b. Okay, so what I mean by this is the inputs times the weights times the bias. Okay, so that's what we do here, and then we add this. So this layer right here, okay, is added onto this one. So when we add this layer to this one, what happens is you further refine the output from this one to using this one. You get what I mean? So this is this is the units. So that's w times b. Okay, so the weights times the bias. So over here, that's why we have two different layers. So this is the first layer, and this is the second layer in this model, in the sequential model that we're calling to this variable, right? So then we have, okay, so this is a compile, like I said. So MSE is used to measure the error, and optimizer, so this is used to go back and optimize the weights and pretty much reduce the errors. And the number of times you want it to iterate is the epochs, and so higher the epochs, the higher the number of times it's going to do. So batch size is the number of sample sizes you're going to give, and this is inputs and labels. I'll get back to this. So callbacks is just to like redraw the graphics every single time. So that's why we use this is wiser basically. So that's just to draw the stuff, right? So pretty much over here, so this is the surface. Surface is like where you want to draw it, and it's like a div generally in JS. And this is where we can put everything together. And this is the batch size, epochs, the shuffle, and the callbacks is to redraw the graphics, right? So we do this thing where we first we normalize data, and then we unnormalize the data. And once we unnormalize the data, we plot the actual data over here. So we see what the what do you call that? What the data is supposed to be, right? So the accuracy once we have fine-tuned it by normalizing it basically. So this is just the basic understanding. So let me show you guys something else. So we know what these linear graphs you know what a polynomial graph is, right? So it's just the opposite of a linear graph. It's just like when you have random scatter plots across a surface, and then you have like dots everywhere, and then you need to draw a best fit curve across a bunch of randomly scattered points. And this is the brain.js the model, and you can use it to train. So as you can see, train with the 4 input objects, and we're expecting an output. So let me show you guys something in terms of detecting. So this is detecting RGB. So what's the output of dark blue? That's what we give with this. So this is the range out of 255. So for dark blue, so this is like RGB, and out of 255, so this is, we're given different inputs, and we're predicting what's the probability of it. So that's seems to be this seems to be the probability, right? So wiser. So I've explained what wiser is as well. What else do we have? Scatters, you know what scatter is. Training, obviously you need to give it more data to train, and then testing. Testing is more of like I don't know if you guys have seen the test.size. Let me show you guys. So when you in this method, in this function, when you give it test. So when you give it 0.2 over here, that means the rest of the data goes to training, as you can see right here, right? So the train test split, for example, this is going to testing, so 20% is going to testing, and the rest of it is going to training. So that means 80% is going to training, as you guys can see. So that's from the overall samples, by the way. So yeah, overall, I think we're pretty much done with this part. So data, let's see what's going on here. So obviously we need data to be pulled from somewhere, so you can just fetch it from like an endpoint, or you can give it a CSV file. So we know about correlation coefficient. So this is like how much of a relationship it is, whether it's positively or negatively, or if there's no relationship whatsoever, like this one right here. And yeah, so this is linear regression, and this is polynomial regression, like I said. And yeah, so apart from that, what I'm also going to show you guys is a few other notes that I've taken. So right here we have the cluster data, so it's obviously put into different clusters. That way it's easier to make judgments out of the data. And this is advanced, but before that I want to show you guys something. So this is obviously the variance calculation. So this is a simplified manner, simplified equation right here. And then we have the square root. So you find you square root the variance and you find the STD, standard deviation, right? And then for correlation coefficient, I think you need to further coefficient. Yeah, so for this, there was something else that we need to do. Let me check something real quick, guys. For example, okay, so over here we have the correlation. So once we have the correlation, so this is the variance and standard deviation. So that's the square root of the variance, obviously. So as you can see, standard deviation divided by mean is the coefficient of variation, not correlation coefficient. So it's the coefficient of variation. That's what it is. So coefficient of variation is the standard deviation divided by the mean. So that's the coefficient of variation, right? It's used to get an idea of how large the standard deviation is. The standard deviation is how spread out the values are from the mean, right? Let me double check. Standard deviation is how spread out the values are from the mean. Yes. Yeah, okay. So what we're going to do here is we're going to use this. So as you can see, we have the standard deviation, we divide it by the mean, and then we get the coefficient of variation. So what we're going to do is we're going to paste this here. So let's say ML, and let's call it coefficient of variation. So let's say, for example, variance first, and then you find the standard deviation, and then from there you find the coefficient of variation, right? So apart from that, we have, what else do we have? Correlation matrix. So I don't understand the difference between, what's the difference between coefficient, coefficient of variation versus correlation coefficient. Let's see what it says. But basically, these are the relationships between x and y axis, as you can see. And so this is just rounded off. That's what it is. And seems like okay. So this method right here does everything, and then you can like pretty much display the data. That's what we're doing here, right? So let's see what else do we have. So causality. So this is the scatter plot. Obviously, it's just to plot that. So this is just to simplify things and to find the correlation between the two. We use this method right here. It seems to be coming from I think it's coming from pandas itself. Yeah. Okay, so what I'm going to do here is probably so plotting. So we know it's x plus b for linear equations, and then we have for the slope it's obviously y2 minus y1 divided by x2 minus x1. So that's like simple stuff, right? So let me just like recap that. So so intercepts, that's where the x-axis meets the y-axis, specifically where in the y-axis, because we're looking for the y-intercept, and because the x plus b. Let's see something. So let's simplify. So in summary, the coefficient of variation is about understanding the relative variability of a single data set, and the correlation coefficient is about understanding the relationship between two different variables, right? Understanding the relative variability between of a single data set, right? The correlation coefficient is about understanding the relationship, right. Okay, so give me a simple two examples for each. So let me grab this real quick, and let me just do ML, and let's say coefficient of variation versus correlation coefficient. Okay, so let's see what the summary of this is. Let me just scroll down real quick. So we have the p-value in the so I got the p-value earlier. P-value. So as you can see, the p-value, it tells if the result is statistically significant, and r-value tells how strong two things are related, right? So there was some sort of a concept here. So let me try it. Okay, so if p-value is low, it suggests that there is a relationship between the two variables. If p-value is high, it means okay. So right, so the p-value needs to be no, but the relationship is 0, meaning no effect. Right. But if there's a, what's the difference between r-value? R tells you the strength and the direction of the relationship. P tells you if the strength is statistically meaningful. Right. But I need like a real, where is it? R-value? I forgot where the R-value was. Let me try to grab that. So I'm gonna try something here. So for example, if R equals 1, it means perfect positive correlation. Right. Okay. So basically, P being greater, so let's simplify this further, right? P being low is good, P being high is bad. Okay, P being low is good, and let's simplify this. P being, let's say this is not related, so ML, P being low is good, R being high is good. P being low and R being high, right? So P being low and R being high is good. Okay, so let me get the example from here as well. This is this one right now. Let me grab this real quick, and let's paste this here. Boom. Okay, so once we have the coefficient of variation, it tells you how much of variability exists in the relation to the mean of a right, and correlation. So basically, the correlation coefficient is obviously like this, the relationship between the data, like x and y axis. So it could be positive relationship, no relationship, or negative relationship. So that's why it goes towards the left side, and if it's positive, it goes to the right side. But then, when it comes to coefficient of variation, it's obviously like the standard deviation divided by the mean. So it tells you how much of a variability there is in the data, right? So from the mean. So let's do. So how divided the data is. So let's say, for example, coefficient of variation versus correlation coefficient. So apart from that, what we're going to do here is pretty much so this OLS is obviously for ordinary linear regression, I believe. So this is the x-axis and the y-axis, and we're combining b duration to it. So so it's x plus b, right? So pretty much what else do we have? This is b, and then times, I don't know what this is, to be honest. What's this? I don't get that. This is ax plus b, ax plus b, and then what is this? I don't understand that. So let's grab this image first, and I'm going to say ml, and I'm going to use right. So let's grab this one first, because this is pretty much the result of this. So I'm going to grab this real quick. I'm going to copy, and I'm going to paste this here, and I'm also going to copy paste. I'm also going to copy this part. So this is obviously, we know this is a, right, and this is x, right, a times x plus b, and then we have whatever this is, which is rounded to 2 decimal points, which is why this is here. So I don't understand why this is here, so that's why I need to try and understand what this is about. So aberrate pulse and the duration. So this is obviously ax plus b, and then why is this here? I'm confused. So let's go back and let's try to get this. So p value obviously r squared. So p needs to be low and r needs to be high. That's the point. See, p needs to be low, p needs to be low, and r needs to be high. R needs to be high. Pussy so low. Now I wanted to sort of like put it in some rap lyrics so that way it goes in my head, but I couldn't. I found the p low, r high, p low, r high. I can't like interpret it into some like real world scenario though, like something that sticks in my brain, not head. Anyways, let me try something here, right? So this is ax plus b, obviously. So as you can see, that's the average pulse. So x is obviously the input, and we're finding the y-intercept, right? So a is the slope, maybe? No, x plus b, b was the, wait, what was it? I forgot the fucking equation. I can't believe that. I actually can't believe that. It's crazy. Let me double check on this. Linear regression. So this is the slope, right? Slope and intercept. So slope plus slope plus input plus slope times input times plus intercept. But let me grab this so that way it sticks in my head. Slope is obviously just one. Slope is 2 minus y1 divided by x2 minus x1. Yes, it should be. Yeah, okay. That's what. Man, I've forgotten this bullshit. So let me, you know, just find like the relationship between. Okay. Yeah. So I mean, I'm fine with this. It's just preparing the data, just getting rid of the null values and shit. Reading the data, getting rid of the null values, and converting the data to a proper data format. So that's what we're doing with the average pulse. Where is it? Average pulse. Convert that, and max pulse convert that. Now it's assigned to this. Now we have everything in one data type. Right. This is how spread out the values are compared to the mean value. Wait, isn't the distribution curve also the same shit at the end of the day? Because the distribution curve is also like negative skewness means values are, wait, let me ask my friend GPT here. Negative skewness means values are more towards negative, more spread towards negative than mean. Yes. Yeah, okay. So positive skewness is obviously the opposite of that. ML, let me just grab this real quick. So definitions, and I'm also going to do something else here. So obviously positive skewness is obviously the values are more spread out towards the positive side, so that's why the distribution curve is like tending towards that side, right? If it's like balanced out, everything is like nearby to the median, I mean the mean values, so that means it's like it's towards the middle range, you know what I mean? Like the values are close by. And there's also the kurtosis, which increases when you give it more samples, and the MSE, the failure, like the rate of what was that called again? We grab that real quick. Kurtosis, I forgot where it was, to be honest. I think it was under like kurtosis, I think it was under distribution. Yep. So if you look at this, for example, so this reduces when you give it and then what was that called again? Margin of error. So margin of error reduces when you give it more data. So ML margin of error reduces when you give it more data. And right here, I'm going to use more samples, and the margin of error obviously reduces, as you can see, and going this way. And kurtosis, so that's what the kurtosis is. So when you give it more samples, it goes the distribution curve basically goes higher and higher and higher. And then this is like when there's While skewness describes an unexpected right, kurtosis this describes unexpected values in both tails, right? So let's say, oh no, there's a different definition here. Skewness describes an unexpected values in one tail. Kurtosis describes unexpected values in both tails, right? So negative kurtosis, now lower than normal distribution. Positive kurtosis higher than normal distribution, right? So let's say negative kurtosis lower than normal distribution. Copy, and positive kurtosis higher than normal distribution. Let me just grab that. Okay, so variability, so this is obviously variance and standard deviation and stuff. So that's how spread out the values are. We've seen that. Variance, standard deviation, and finding the correlation. What was it? Coefficient I gotta study this properly. Coefficient, what was it? Coefficient of variation. Coefficient of variation, that's crazy. I gotta refer to this again. So let me just grab that. And we'll grab this real quick. Coefficient of variation. So yeah, that's pretty much it. And obviously we have the mean, mode, median, usual stuff. Outliers, which are outside the usual values, like anomalies basically. And we have the matrices obviously, and the tensors, which are 2D, like n-dimensional arrays. So n-dimensional matrix, that's what it is. And you see this over here. So tensor is an n-dimensional matrix, scalar is a 0-dimensional tensor, a vector is a 1-dimensional tensor, and a matrix is a 2-dimensional tensor. So let me grab a, so in dimensional spaces. Number of directions a tensor can have in n-dimensional space is called the rank of the tensor. So rank is denoted R, scalar is a single number, and interesting, so all above are tensors, but when we speak of tensors, we generally speak of matrices with a dimension larger than 2, right? So, interesting, okay, I'll refer to this again, so it goes in my head. So let me try grabbing a simple note right here, and let me try, let's say, for example, ML. Let's do a tensor is an n-dimensional matrix, and we also have tensor ranks. And let me grab this real quick. And let's say, for example, ML, tensor ranks, and a number of directions a tensor can have in a n-dimensional space is called the rank of the tensor, and the rank is denoted in R. And right, so tendency, real tensors, all of the above are tensors, but when we speak of tensors, we generally speak of matrices with a dimension larger than 2, right? Interesting. So these are the tensors, so operations, and that's adding different tensors. So subtraction, obviously. So it's like matrices basically, except in like code, because you can't like write matrices in code, right? Tensors are the way of interpreting matrices in code. Yes. Matrix is a 2D array. Right. Right. Okay. A vector, 1D tensor, a matrix, 2D tensor, 3D tensor, right? A matrix is specifically a 2D tensor. A tensor can represent multidimensional data, not just 2D. So matrices are just a subset of tensors. Interesting. So, functions. So this is the max and the min and the mean, obviously. So apart from that, guys, what we're going to do is we're going to try to understand, obviously we know what vectors are. So we have the vectors and the matrices. So we had some definition here. So a vector is a 1-dimensional tensor. A matrix is a 2-dimensional tensor, right? So we have 2D, and this is 1D. So it's just to one side. And a scalar is a 0-dimensional, so there's no dimensions, it's just here. So 1 dimension, so that's one way. And then 2-dimensional, which is 2 ways. And then we have 1 tensor. A tensor is a generalization of vectors and matrices to higher dimensions. Right. So a tensor can fit different sizes, I'm assuming. So a tensor pretty much can account for different sizes of matrices. Yes. Right. Okay. Also extends to 2D matrices to represent data in a higher dimensions. Right? Scalar is obviously 0D tensor. Right. 2D tensor. 3D tensor. Yep. This is just one way, and then we have 2 ways, and then we have 3D tensor, which is a cube of matrices, right? So let me just grab this real quick. So let's say, for example, ML tensors can be 0-dimensional, 1-dimensional, 1 way, and 2-dimensional, which is goes 2 ways, and cubed. So that's 3D cubed. Okay. So apart from that, what else do we have? Transposing a matrix. So this is obviously just don't switch. That's the concept. So it's just don't switch. And what else do we have? Visor is obviously just to plot and the operations and the models. The tensors are needed, and then you use the operations on the tensors, and then you create models out of them by normalizing the data, and then refining the data further using models, and then you pretty much, what else do we do? Yeah, you compile them, and then you reduce the error with the higher number of epochs. You get it to use the model, and once it's fully done, and once you unnormalize the data to normal values. So let me write the definition on here so that way first it can be data and then normalized level normalize, compile, increase epochs to reduce the MSE, compile, add layers to a model, compile, increase epochs to reduce the MSE, normalize, what, yes, am I missing a few steps here? Mostly correct, right? Shuffle the data, normalize, standardize the data, so this is what I said, and evaluate the model. Right, so the optimizer obviously goes back and then adjusts the weights, and then it usually reduces the MSE, and that can be sort of done, so the higher number of times. So overfitting is obviously when the model is too complex, and underfitting is when the model is not complex enough to understand what's going on. So in summary, you clean and split the data, shuffle and normalize the data, build the model, add layers, define activation functions, loss function, optimizer, right, MSE and SGD in this case, and compile the model, train the model, increase epochs if necessary, evaluate on validation set, and normalize predictions if needed, and plot the results, test on test set, optionally fine tune the model. Right, so let's grab this real quick. You can create, train, and evaluate a machine learning model to solve regression or classification problems. Right, let me know. Life cycle. So, show me some code sample. I'm a beginner ML guy, so keep it simple. Okay. Test size is 20%, and we have the transform the test, right? Why is it transforming the test? Right? This is just normalizing data, I believe. So we have the training and the testing, obviously. So this is Python code, so that's why it's a little different. So we have a sequential model called over here. Optimized is obviously Adam in this case, and the loss is MSE. So at first we were looking at stochastic gradient descent, but right now we're looking at Adam, which I'm not too familiar with. Box 100. So it's only just one sample here. Validation data, right? There's the testing data to validate it, and there's the training data. So we're splitting, I think, 20%, 20%. And evaluate the model, the testing data, and then plot the actual model. Predictions, model.predict, xtest. Right, let's see what this results in. Key concepts covered. So let me grab this real quick. Training. Evaluation, measuring how well model performs. Visualization, plotting lost track progress. Indeed, let me copy this real quick. Let me grab email. So let's run this real quick. Let me what's good on here? I'm not too sure about why this is happening, but seems like it's fucking up. I can't send it. I'll upload it as a file. I think I'm gonna, yeah. Cool. Interesting stuff. So let's say, for example, ML, and then we'll do, where is it? Training and test sets. So this is 20%, and this is 80%. I'll just say R, because it's the rest of the data, normalized data. So it's basically using the min-max algorithm, neural network, and then compile the model. So this is the loss and the optimizer, and then we have the training model. So training model, right, evaluate and visualize the results. It's just using stuff like, you know, you get the point. Pointer. Right. Training model. So let me say, let's see what it says. Yep. Right, okay. So, training the model. Right. Right, okay. Training data and then testing data. You first have that over here. Train test split right here. So the testing data, training data, test size. You give it the actual values. So that's x and y. That's over here. You have the min max. I mean the normalizing the data. The sequential model. We have the two layers. So this is x xb, xw and b. Where is it? Activation? No, this is just x and it's just one layer, isn't it? Yeah. Optimizers and MSE epochs to number of times, number of iterations, number of sample size, and validation data, training data. You fit the model, you evaluate the loss using the test data, you plot the data, and you use the predictions with the trained model. So also over epochs, right? Loss MSE predictions model dot predict, right? Predictions with the test trained model, predictions on test data, predictions on flatten actual, right? Let me copy something here. So we have the data, we have the training and testing data set, we have the normalizing, and we have the sequential model, we have the compiler, and we have the loss calculation, we have the epochs, number of times it's going to repeat itself, validation data, so obviously we have the x testing and the y testing, and we have the training data, and we have the evaluation of the model over here, the loss function, and we plot the data, and we predict using the x test, and once we do that, let's run this. Let's see if it works. Okay, so it seems like it's calculating the loss right here. So loss function is pretty much over here, and training data, validation loss, right? So the loss is less on the validation loss compared to the... I don't understand what the validation loss is. So we obviously have this one, right? Which is the validation loss. So it's coming from history, which is this one. And... right, I need to understand what's going on here. So I'm gonna get like a picture here, saved on my computer. I'm gonna call it loss.png. There we go. So yeah, I mean, predictions on test data, actual test data values, but this is because it's more normalized, isn't it? Because these values are like spread out, right? So I mean, it's all right. Let's see. I'll just call you LOL. And yeah, I mean that's enough for now. Try again in a little while. I hope this video was entertaining. I don't know if it was, but I'll see you guys later. Bye bye.